Welcome to another deep dive, everybody. Today,
Hmm.
we're going to be looking at high-order derivatives,
Oh, yeah. Yeah.
especially in the context of physics-informed neural networks.
PNNs.
DNNs, exactly right.
Yeah. So high order derivatives, those are really difficult to calculate.
Yeah.
And luckily, we have a new method that's come out called the Stochastic Taylor Derivative Estimator, or STDE.
Okay, so we're talking about PNs and high-order derivatives and a solution called STDE.
Yeah.
Before we get too far, can we just step back and talk about PNNs again?
Yeah, absolutely. So PNNs are neural networks that are trained to solve PDEs, so partial differential equations.
Right, those are like equations that describe how things change over space and time.
Exactly.
Okay, so PNNs are kind of like detectives who figure out the rules of physics. But why are these high-order derivatives such a problem?
So derivatives are obviously something we've used for a very long time in calculus.
Yeah.
But when we're dealing with PDEs, oftentimes we need to calculate derivatives that are beyond the first or second order. So going to higher orders like third, fourth, fifth order, and traditional methods like back-propagation, they just don't do very well when we get to those high orders.
So it just becomes too computationally expensive.
Exactly. It just takes way too much memory.
Gotcha. And that's where STDE comes in.
Exactly.
Okay, so STDE, this new method, can you give us a sneak peek of how it works?
Yeah, so imagine like instead of trying to solve a giant Sudoku puzzle at once, you break it down into smaller chunks.
Okay.
That's kind of what STDE does. It takes these complex derivatives and it approximates them
Okay.
without having to calculate the entire tensor.
Okay, but how does it do that?
Well, it starts with something called the Taylor series.
Okay.
Don't let the fancy name intimidate you. It's essentially just a way of representing a function as a sum of terms.
So instead of looking at the whole picture, you break it down into little pieces.
Exactly.
Okay, and how does that help us?
So STDE uses the Taylor series to take what are called snapshots of the function. And based on these strategically chosen points, it can estimate the derivative.
So it's kind of like if you want to figure out how fast a car is going, you just look at its position at different points in time.
Exactly. And what's really amazing about STDE is that it can handle not only high-order derivatives, but also high-dimensional problems.
Oh, wow. Yeah.
So two of the big problems that we face.
Okay, that's really interesting.
Yeah.
Now, the paper mentioned something about random jets.
Yes.
Can you explain what those are?
Yeah, so random jets are essentially a set of instructions
Okay.
that tell us how to move through this high-dimensional space.
Okay, so they're kind of like tour guides. They help us explore this really complex mathematical space.
Exactly.
And the paper talks about sparse and dense jets.
Yes.
What's the difference?
So imagine you're planning a trip, right?
Okay.
You can have a very detailed itinerary that covers every single landmark. That would be like a dense jet.
Okay.
Or you could have like a streamlined itinerary that focuses only on the must-see places. That would be like a sparse jet.
Okay.
So choosing between them depends on the trade-offs that you're willing to make between accuracy and cost.
So when would you choose one over the other?
So sparse jets are really good when you want a good balance between those two.
Okay.
So if you want to get the most out of your trip without wasting time on detours, that would be like a sparse jet.
Right. Okay.
But dense jets, those come in handy when you're dealing with operators that have a high degree of something that we call off-diagonalness.
Off-diagonalness.
Yeah, it's a mouthful, I know, but it refers to how much your operator mixes partial derivatives.
Okay.
And so for those kinds of situations, dense jets are going to be better
Okay.
because they cover more of that space.
Right, they explore every little corner.
Exactly.
But is there a downside to using dense jets?
Yeah, they are a bit more computationally expensive.
Okay.
And in some cases, for certain operators, it may not even be possible to construct a dense STDE.
Okay.
Yeah.
Now, the paper gave a specific example of where sparse jets work really well, and it mentioned something about a Laplacian.
Yes, the Laplacian is something that appears in a lot of different PDEs. It's essentially an operator that measures how quantity is changing in all directions.
Okay.
So think about like how the wind is blowing from
Wow.
all directions, not just north or south.
Okay.
So the Laplacian is really good at that. And STZE, with its sparse random jets, it can handle the Laplacian really well.
Okay.
So it's almost like a specialized weather vane that can tell you the wind direction and speed from all directions.
Okay. That's really cool. So we've got PNNs, which help solve these PDEs, high-order derivatives, which make things really difficult, and STDE, which comes in with its approximations and its random jets to solve those problems.
Yeah,
It's almost like a mathematical action movie.
I like that analogy.
But before we get too far ahead of ourselves, what is the real-world impact of this? Why should anyone care about this?
Right. So STDE isn't just about making things faster. It's really about being able to solve problems that we couldn't solve before.
Okay.
So imagine being able to simulate climate patterns so well that we can predict future changes with much better accuracy.
Oh,
Or being able to design personalized medicine, simulating how drugs would interact on a molecular level.
that's really incredible.
Right. So being able to tailor treatments to an individual's genetic makeup, that's really what we're talking about.
This could revolutionize fields like climate modeling and drug discovery.
Absolutely. These are very complex systems that are governed by PDEs, and oftentimes these PDEs are high dimensional.
Right.
So with STDE's ability to handle these high-order derivatives and this high dimensionality, we can unlock the secrets of these systems.
So it's like we've been given a key to understanding these systems.
Exactly.
Now I'm really curious to know how this performs in practice. What kind of results did the researchers find?
So they tested STDE on a variety of different PDEs, and the results were really amazing.
Okay.
In some cases, it was over 1,000 times faster and used 30 times less memory.
Really, the previous state-of-the-art methods.
Wow, 1,000 times faster. That's incredible. What kind of problems were they able to solve that weren't possible before?
So one really cool thing they did was they solved a 1 million dimensional PDE.
Wow, 1,000,000 dimensions.
Yeah, so previously this was just way too big
Yeah.
for us to even consider.
Yeah.
And they were able to do that with much less memory.
So it's faster, it's more efficient, it can solve problems that weren't solvable before. This is really impressive.
Yeah, it's really a game changer.
Now I'm kind of curious about this Taylor mode automatic differentiation.
Yeah.
It sounds kind of intimidating. Can you break that down for us?
It's not as complex as it sounds.
Yeah.
Remember those really big derivative tensors that we were talking about earlier?
Yeah.
Taylor mode AD is basically a way to calculate those high-order derivatives
Okay.
without having to compute the entire tensor.
So it's like we have a special tool that can just pull out the information that we need.
Exactly.
And STDE combines Taylor mode AD with these random jets.
Okay.
And it uses the Taylor mode AD to kind of push forward these jets, essentially helping them explore this mathematical space.
All right. So it's like giving our explorers a map and a compass.
Exactly.
So they know where to go.
Yeah.
Okay. And so choosing between the sparse and dense jets,
Right.
that depends on the differential operator.
Exactly.
So for something like the Laplacian,
Yeah.
sparse jets work well.
Yeah, for the Laplacian and a lot of other common operators, sparse jets are really the way to go.
Okay, but when would we use the dense jets?
So dense jets, remember, those are more computationally expensive.
Yeah.
So we want to use those when we have operators that have this high degree of off-diagonalness.
Right, like our mixed martial arts fighters.
Exactly. So
Yeah.
they're a little bit better at handling those more complex situations.
But there are limitations to using those.
Yeah, so for operators beyond the second order, it might not even be possible to construct dense STDE. Yeah, and also they looked at some really cool cases where they applied this to higher order PDEs. So things like the 2D Korteweg-de Vries equation, the 2D Kadamtsev-Petviashvili equation.
Okay.
These are equations that are used to model nonlinear wave phenomena. So there's really cool waves that can travel long distances without changing their shape.
That's so cool.
Yeah, and they even looked at a gradient enhanced version of the 1D Korteweg-de Vries equation.
Gradient enhanced, what does that mean?
So this is a technique called gradient enhanced PNNs or GPINs. And essentially what this does is it adds what we call a regularization term to the PINN.
Okay.
And that regularization term encourages smoother and more accurate solutions.
Okay, so it's like adding a quality control step to
Exactly.
make sure the PIN is doing what it's supposed to do.
Right, but this regularization term involves calculating something called the gradient of the residual. So the residual is the difference between our prediction and the actual solution.
Okay.
And so we have to take the gradient of that, and this adds more computation.
Right, so was STD able to handle that added complexity?
Yeah, so they found that STDE really sped up the computation of these mixed partial derivatives, which made it possible to apply these GPINNs to these higher order PDEs.
Okay.
And they showed that it outperformed a traditional method, which was based on what we call repeated applications of back-propagation.
Wow, so not only is it efficient, but it opens up new possibilities.
Exactly.
Now, remember the paper mentioned something about reducing the memory requirements,
Yes.
especially for these really big high-dimensional problems.
Yeah, so that technique is called weight sharing.
Weight sharing, okay.
It's a way to reduce the number of parameters in the neural network.
Okay.
And that's especially important in the first layer because that's usually the bottleneck for
Uh-huh.
memory.
So how does that work?
So instead of having a separate weight for every single input dimension in that first layer,
Okay.
what they do is they use what's called a convolutional layer
Okay.
with a specific stride and filter size. And this allows them to share weights across these different dimensions.
Sounds like we're being very efficient with Akadigi.
Exactly.
Or we're grouping similar items together so we don't have to take as many bags.
Right, right.
Did they test this out?
Yeah, they tested this on a very high-dimensional problem called the inseparable Allen-Cahn equation.
Okay.
And they found that this weight sharing could reduce memory by a factor of 2.5 without sacrificing accuracy.
That's incredible.
Yeah, and they were even able to solve a 5 million dimensional PDE using this technique.
5 million dimensions. Wow.
Yeah,
That's amazing. It's like we're exploring the universe with a simple star chart.
exactly.
So we've talked about how STDE uses Taylor mode AD, random jets to approximate these derivatives. We've seen how it performs better than previous methods. It can solve problems that we couldn't solve before. It can even incorporate things like weight sharing to push the boundaries even further.
Yeah.
So what's the takeaway here?
So the takeaway is that high-order derivatives are really important for accurately modeling these complex phenomena, but they're really hard for computers to compute.
Yeah.
STDE gives us a way to approximate these derivatives using the Taylor series, randomization, and these random jets.
Okay.
And it does this with incredible speed and memory improvements, which allows us to solve problems that were previously impossible.
That's amazing. And this research is really a call to action for everyone to explore these new possibilities and push the boundaries of what's possible.
Absolutely. It's like we've been given the key to this treasure chest of solutions,
Yeah.
and it's up to us to go explore it.
Now, are there any limitations to STDE?
Yeah, so while STDE is great at handling high-order derivatives on the input,
Okay.
it's not as good when we're dealing with high-order derivatives on the parameters of the network itself.
Okay.
So that's one area where we can improve.
So it's like our car can go off-road, but it can't park.
That's a good analogy.
Okay.
Yeah, so one thing we can do is explore what are called variance reduction techniques. So remember, STDE uses randomization.
Yeah.
And whenever you use randomization, you introduce variance.
Right.
So if we can reduce that variance, we can potentially make STDE even more accurate and reliable.
So it's like trying to hit a bullseye.
Right.
The less variance, the more likely you are to hit it.
Exactly.
Okay, what other research directions are there?
Another really cool area is exploring connections between STDE and what's called randomized numerical linear algebra.
Okay.
This is a field that uses randomization to solve big linear algebra problems.
Okay.
And there could be some really cool synergy there.
So it's like we're building our team of superheroes,
Exactly.
and they each have their own unique abilities.
Yeah, and the paper also hints at applications beyond PNNs and scientific modeling.
Oh, really?
Yeah, so they mention areas like adversarial attacks, feature attribution, and meta-learning, all areas within machine learning where high-order derivatives are important.
Oh, wow.
So imagine building AI systems that are more secure and less susceptible to these adversarial attacks.
Right. That's really important as we're seeing more and more AI being used in everyday life.
Exactly. So we want to make sure that these AI systems are safe and reliable.
Yeah. What about feature attribution?
So feature attribution is about identifying which features are most important for a model's prediction.
Yeah.
So let's say you're building a model to predict housing prices.
Good.
Feature attribution might tell you that the number of bedrooms is more important than the color of the house.
Right.
And higher-order derivatives can really help us in this process.
So it's like having a detective who can point out the most important evidence.
Exactly. And STDE can make these calculations a lot more manageable.
Okay. That's really cool. And then finally, meta-learning.
Yes, meta-learning.
What's that about?
So in meta-learning, the goal is to build models that can learn new tasks very quickly
Okay.
with as little data as possible.
Okay.
And this often involves optimizing the learning process itself,
Right.
and high-order derivatives can help with that.
So it's like we're teaching the AI how to be a better learner.
Exactly. We're giving it the tools to learn and evolve.
Okay. And STDE can help speed up this process.
Yes, it can really accelerate the development of these meta-learning algorithms.
Wow. So this one technique has so many different applications. It's really incredible.
It's really a game changer.
It's like a ripple effect that's spreading out and creating new possibilities everywhere.
Yeah.
But let's bring it back down to earth. Can you summarize the key takeaways from this deep dive?
Sure. So the main takeaways are that high-order derivatives are essential for modeling these complex systems, but they're really hard to calculate.
Right.
STDE gives us a way to estimate these derivatives using Taylor series, randomization, and these random jets.
Okay.
And it does this much faster and with much less memory than previous methods, allowing us to solve problems that we couldn't solve before.
Okay, and this research is an invitation for everyone to explore these new possibilities.
Absolutely.
It's like we've been given this amazing new tool, and now it's up to us to go out and see what we can do with it.
Exactly, and I would challenge our listeners to imagine a world where STDE is widely adopted. What breakthroughs have been made? What problems have been solved? Share your thoughts with us, and let's see what the future holds.
That's a great challenge. Thank you so much for joining us on this incredible deep dive into the world of STDE. Until next time, keep exploring, keep learning, and keep asking those big questions.
Yeah, it's really about being able to solve problems we couldn't solve before. Like,
Right.
imagine being able to simulate climate patterns with, like, so much detail we can predict future changes
Wow,
with, like, much greater accuracy.
that'd be
Or
incredible.
being able to design personalized medicine, simulating how drugs would interact at a molecular level,
Wow.
right? Being able to tailor treatments to an individual's genetic makeup, that's what we're talking about.
So this could like revolutionize fields like climate modeling and drug discovery.
Absolutely. These are very complex systems that are governed by PDEs, and oftentimes these PDEs are very high dimensional. So with STE's ability to handle these high order derivatives and this high dimensionality, we can unlock the secrets of these systems.
It's like we've been given a new lens to see into these systems.
Exactly.
Now I'm curious to know how this performs in practice.
Well,
What did the researchers find?
so they tested STDE on a variety of PDEs, and the results were really amazing.
It's okay.
In some cases, it was over 1,000 times faster
Right.
and used 30 times less memory.
1,000 times faster.
Yes.
Wow, that's like going from a horse and buggy to a supersonic jet.
Exactly.
What kind of problems were they able to solve?
So one really cool thing they did was they solved a 1 million dimensional PDE.
1,000,000 dimensions.
Yeah. So previously that was just way too big to even consider.
Right.
And they were able to do that with much less memory.
Okay, so faster, more efficient. It can solve problems that weren't solvable before.
Exactly. A game changer.
Now, I'm kind of curious about this Taylor mode automatic differentiation.
Yes.
Can you break that down?
Yeah, so it's not as complex as it sounds. Remember those really big derivative tensors we were talking about?
Yeah.
Taylor mode AD is a way to calculate those high-order derivatives without having to compute the entire tensor.
So it's like we have this tool that can just like pull out the information we need.
Exactly.
Okay.
STDE combines Taylor mode AD with these random jets.
Oh,
It uses the Taylor mode AD to push forward those jets, essentially helping them to explore that mathematical space.
so it's like our explorers now have a map and a compass,
Exactly.
so they know where to go.
Yeah.
And so choosing between those sparse and dense jets depends on that differential operator.
Exactly.
So for something like the Laplacian sparse jets work well.
Yeah, for the Laplacian and for a lot of other common operators, sparse jets are good.
Okay, when would we use the dense jets then?
So remember, dense jets are more computationally expensive.
Right.
So we want to use those when we have operators that have that high degree of off-diagonalness.
Right, like our mixed martial arts fighter.
Exactly.
Okay.
So they're better at handling those more complex situations.
But there are some limitations to using them.
Yeah, for operators beyond the second order, it might not even be possible to construct dense STDE.
Okay.
Yeah. They also looked at some cases where they applied this to higher order PDEs. So things like the 2D Kordovec-de Vries equation, the 2D Kadomtsev-Petviashvili equation. Those are used to model those nonlinear wave phenomena.
So they're the cool ways that can travel long distances without changing shape.
Exactly.
Okay, cool.
And they even looked at a gradient-enhanced version of the 1D Kordovec-de Vries equation.
Gradient enhanced, what does that mean?
Yeah, so it's a technique called gradient-enhanced PNNs or GPINNs, and essentially what it does is it adds this thing called a regularization term to the PIN,
Okay.
and what that does is it encourages smoother, more accurate solutions.
So it's like adding in a quality control step.
Exactly, to make sure the PIN is on the right track.
Okay.
But that regularization term involves calculating something called the gradient of the residual. And the residual is like the difference between our prediction and the true solution.
Right.
And we have to take the gradient of that, and that adds more computation.
Okay, so was STDE able to handle that added complexity?
Yeah, they found that STDE really sped up the computation of those mixed partial derivatives, which allowed them to apply these GPINs to these higher order PDEs.
Oh,
And they showed that it outperformed the traditional method, which is based on like repeatedly applying back-propagation.
so it's not only more efficient, but it opens up new possibilities.
Exactly.
Now, the paper mentioned something about reducing memory requirements
Yes.
for these high-dimensional problems.
So that's called weight sharing.
Weight sharing, okay,
It's a way to reduce the number of parameters in the neural network.
okay.
And that's particularly important in the first layer because that's where the bottleneck is for memory.
So how did that work?
So instead of having a separate weight for each input dimension in that first layer, they use something called a convolutional layer with a specific stride and filter size. And this allows them to share weights across those different dimensions.
So it's like we're being very efficient with our packing
Exactly.
and grouping similar items together.
Right.
Did they test this?
Yeah, they tested it on a really high-dimensional problem called the inseparable Allen-Kahn equation.
Okay.
And they found that weight sharing reduced memory usage by a factor of 2.5
Wow.
without sacrificing accuracy.
Well, that's awesome.
And they were able to solve a 5 million dimensional PDE using this technique.
5 million.
Yeah.
Wow. That's amazing. It's like exploring a universe with a star chart.
Exactly. It highlights how this weight sharing technique, when combined with the power of STDE, can unlock these really large-scale problems.
So we've talked about how STDE uses Taylor mode.
Yeah.
Random jets, approximates derivatives, performs better than traditional methods, can solve problems we couldn't before, and incorporate things like weight sharing to push the boundaries further.
Yeah.
What's the takeaway?
So high-order derivatives are super important for modeling complex systems, but they're hard to compute. STDE gives us a way to estimate these derivatives using Taylor series randomization and those random jets.
Yeah.
It does this faster and uses less memory than other methods and lets us solve problems that were previously impossible.
Amazing. And it seems like this research is an invitation for everyone to explore these new possibilities.
Absolutely.
It's like we've been given this really amazing tool, and now it's up to us to go and see what we can do with it.
Exactly. And I would challenge our listeners to think about a world where STDE has been widely adopted.
Okay.
Like what amazing breakthroughs could be made, what problems have been solved. Share your thoughts and let's see what the future holds.
I love that challenge.
Yeah.
Thank you so much for joining us on this deep dive into STDE.
Absolutely.
Until next time, keep exploring, keep learning, and keep asking those big questions.
Yeah, it's not as good when we're dealing with high-order derivatives on the parameters of the network itself.
Okay, so there's room for improvement there.
Yeah.
It's like our car can go off-road, but it can't parallel park.
Exactly.
Yeah.
Yeah, so one thing we could do is explore these variance reduction techniques.
Variance reduction techniques. Okay.
So remember how STDE uses randomization?
Yeah.
And whenever we use randomization, that introduces variance.
Right.
So if we can find ways to reduce that variance, then we can make STDE even more accurate and reliable.
So it's kind of like hitting that bullseye.
Mm-hmm.
The less variance you have, the better chance of hitting that target every time.
Exactly.
What other research directions are there?
Another really cool area is exploring connections between STDE and something called randomized numerical linear algebra.
Okay.
So this field uses randomization to solve like really big linear algebra problems.
Oh, okay.
And so there could be some synergies there.
Yeah, so it's like we're assembling our team of superheroes, each with their own unique abilities.
Exactly right. Yeah. And the paper also mentions some applications beyond PINs in scientific modeling.
Oh, really?
Yeah, they mentioned things like adversarial attacks, feature attribution, and meta-learning, all areas where high-order derivatives are important. So, like, imagine being able to build AI systems that are more secure and robust and less susceptible to these adversarial attacks.
Right. That's becoming more important every day as we see AI used in more and more aspects of our lives.
Right, exactly. We want to make sure that these systems are reliable and safe.
What about feature attribution?
So feature attribution is about figuring out which features in our data are the most important for our model's prediction.
Okay.
So for example, if you have a model that's trying to predict housing prices,
Okay.
feature attribution might tell you that the number of bedrooms is a more important feature than the color of the house.
Right. That makes sense.
And high-order derivatives can help with this.
Okay, so it's like we have this detective that's pointing to the most important clues in the case.
Exactly right. And STDE can make those calculations more tractable.
Very cool. And finally, meta-learning.
Yeah, meta-learning.
What is that?
So meta-learning is about building models that can learn new tasks very quickly with as little data as possible.
Okay, so it's like we're teaching AI to become super learners.
Exactly, giving it the tools to learn and evolve rapidly.
And STDE can help with this.
Yeah, STD can play a role in accelerating the development of these meta-learning algorithms.
That's incredible. So one technique can have such a huge impact on so many different fields. It's really amazing.
Yeah, it's really a game changer.
It's like throwing a pebble into a pond, and the
Yes.
ripples just keep spreading out.
Exactly.
Okay, so let's bring it back down to earth for our listeners. Can we summarize the key takeaways from this episode?
Yeah, so the big takeaways are that high-order derivatives are essential for modeling these complex systems, but they're really hard to calculate.
Right.
STDE gives us a way to estimate these derivatives using Taylor series randomization and these random jets.
Yeah.
And it does this much faster and with less memory than previous methods, allowing us to solve problems that were impossible before.
That's amazing. And this research really feels like a call to action for scientists to explore these new possibilities and
Absolutely.
really push the boundaries of what's possible.
Yeah, so I would challenge our listeners to think about a world where STDE is widely used. What breakthroughs have been made? What problems have been solved?
I love that challenge for our listeners.
Yeah, share your thoughts with us and let's see what the future holds.
Yeah, that's awesome. Thank you so much for joining us for this deep dive into the world of STD. Until next time, keep exploring, keep learning, and keep asking those big questions.